I was enjoying my experience of encroaching the children's world, but I had to be cautious, particularly when the merry-go-round was rotating very fast. I was holding on to the anchors very tightly, and I was having a feeling that a force acting away from the center of rotation was throwing me outward. Now, what is this force which acts only when the merry-go-round is rotating, and it acts away from the center of rotation? The frame of reference attached with a body moving in a circle is called a rotating frame of reference. Its velocity continually changes direction. Due to the change in direction of the velocity, it experiences an acceleration towards the center of the circle. This is known as the centripetal acceleration, and the corresponding force, the centripetal force. The centripetal force acts towards the center of the circle. So, it was not that force which was throwing me out of the merry-go-round. Now, let us try to understand this force using a simpler rotating frame of reference. Here I have tied a string with a ball. Now, as I rotate it, you can see the string is taut. So, the string is under tension. It is this tension force which provides the necessary acceleration towards the center. But for an observer at rest on this ball, it is at rest. However, for that observer too, the string is taut. This is because a force equal and opposite to the tension acts radially outward. This force is called the centrifugal force, and it can be experienced only by an observer at rest or moving with respect to a rotating frame of reference. Now, you can see it more clearly with the help of this thing. Here, I have tied a ball with a rubber band, and now as I rotate it, you can see the radius of the circle is much greater than the original length of the rubber band. This is because the centrifugal force acts in the radially outward direction, and it is this force which was throwing me outward of the merry-go-round. This force appears only in a rotating frame of reference. It is called inertial force, and it is non-existent for an inertial observer. Now, who is an inertial observer? An observer on which no force is acting. According to Newton's first law of motion, such an observer will either be at rest or will be moving along a straight line with uniform velocity. According to Sir Isaac Newton, the observer who is either at rest or moving with a uniform velocity with respect to the distant stars is an inertial observer. Two observers who are either at rest or moving with uniform velocity with respect to each other are inertial observers with respect to each other. When one of them is in the process of gathering speed, that is accelerating, then they are non-inertial with respect to each other. In other words, an observer who is accelerating is non-inertial. Any observer has an acceleration, so such observer is non-inertial. Determining the total observer will have to the inertial forces in addition to the usual forces. But is it worth taking the additional toll of the inertia? But perhaps we can't afford to do that, as We happen to be on a rotating frame of reference, our good old Earth. It rotates about its own axis and revolves around the Sun in an elliptic orbit.
The centrifugal force plays an important role in explaining why the Earth is not a perfect sphere but an oblate spheroid, flattened at the poles and bulging out at the equator. This model here illustrates that effect. Here we have 4 metallic strips which on revolution look like a sphere. However, if I spin them fast, you see that they bulge out at the equator and flatten at the poles like an oblate spheroid. Now the expression for the centrifugal force is minus m omega cross r. Here m is the mass of the particle, omega is the angular velocity, and r is the position vector of the body about a suitable origin on the axis of rotation. For a particle executing uniform circular motion, r lies on a plane if the origin is made to coincide with the center of the circle. Omega is always perpendicular to this plane. So the magnitude of omega cross r becomes omega square r. Hence, the force is m omega square r, where m is the mass of the particle, omega is the angular speed, and r is the radius of the circle. For every point on the Earth, omega is the same, but r is maximum at the equator and minimum at the poles. Hence, the centrifugal force is maximum at the equator and it vanishes at the poles. Since at the time of formation, the Earth was in a fluid state, the force of cohesion was small and could not balance the centrifugal force. Hence, the Earth bulged out at the equator.
The expression for centrifugal force is m omega square r. Now for constant omega and r, it increases with m. This principle is utilized in a centrifuge. Now, I have taken a solution in a test tube. You can see that there are suspended particles in it. Now, I want to get the suspended particles separated from the solution. And to speed up this process, we use this centrifuge. Now I shall place this test tube in this socket. In the stationary position of the centrifuge, the test tube is vertical. Now I'll rotate the centrifuge. You can see that it becomes horizontal. Now when the centrifuge is rotating very fast, the centrifugal force which is acting in the outward direction is much greater than the weight of the suspended particles. And so the resultant of the centrifugal force and the weight is almost equal to the centrifugal force, and for that the suspended particle settles towards the bottom of the tube. Now as you can see, the particles have got separated and has settled down into the bottom of the test tube. Now this principle is utilized extensively by the scientists for separating microscopic particles like viruses, hormones from solutions. Now we have seen the variation of centrifugal force with mass. Now in the expression m omega square r, if we keep m and r constant, then the force varies with omega. And for a high angular speed, this force is high. This principle is utilized by a motorcyclist when he is performing the globe of death in a circus. The motorcyclist does not fall when he reaches the topmost point because his overall weight, inclusive of the motorcycle, is less than the vertical component of the centrifugal force.
Now I will perform an experiment that Newton did 3 centuries ago. I have taken some water in this bucket. Some color has been added to it, and the level of the water is up to this red line, and it is flat. This bucket is hanging by a rope which has been given a twist. Now I will let this bucket go, and the rope will unwind and the bucket will start spinning. Notice that as it spins, the level of water rises above the red line and it dips in the middle. That is, it becomes curved. This happens because the centrifugal force pushes the water particles towards the boundary and they begin to rise, and it correspondingly dips in the center. It means that water, when it was spinning in this bucket, was in a non-inertial frame, and the inertial force, the centrifugal force, was acting on it. Now, as soon as the bucket comes to rest, allow some time for water to settle down, you will notice that the surface of water again becomes flat up to this particular level. Because water comes to rest, it becomes again an inertial frame and the centrifugal force disappears.
The children are now playing with a different merry-go-round. Now will you please allow me to perform an experiment? So far we have dealt with bodies at rest with respect to a rotating frame of reference. Now what about a body having some velocity with respect to a rotating frame of reference? With the help of this channel, I will now impart a velocity to this ball. The merry-go-round is now stationary. You can see that it moves along the radial direction. That is, in the direction of this arrow. As you can see once again, it moves in the direction of this arrow. When the merry-go-round is rotating in the sense indicated by this arrow, and if I impart velocity to this ball, it gets deflected from the original path. According to the non-inertial observer, the ball gets deflected. Is the deflection due to the centrifugal force? Definitely not, because the deflection takes place towards the right side of the original path. Now let us try to explore this force.
It is a rotating frame of reference similar to the merry-go-round. Let us now see what happens if I put a coin on this and make the coin move radially outwards. Suppose first that this disc is at rest and this coin is moving radially outwards with a velocity v. So let us suppose that at time t, the coin has moved to a point O, and then at time t plus delta t, it has moved to a point A. From O to A, the time taken is delta t. Now if the velocity of the coin is v, then the distance travelled is v times delta t. Suppose the disk is moving with an angular velocity omega about the vertical axis. Now the coin will find itself not at point A but at some point B if it happen to be at O at time t. So let us try to estimate the lateral displacement from A to B. So this angle AOB we'll call delta theta, and we will assume that during the time delta t, the radius vector OA has changed direction to OB. So we have delta theta equal to omega delta t. And therefore AB, which is equal to, we will call it delta S, AB, which we will call delta S, this is equal to, according to our formula, V delta t, which is the distance OA, times delta theta, which works out to be omega V delta t squared. Now, if we compare this expression, delta S equal to V omega delta t square, with a linearly accelerated object, then we know that if the object starts from rest, then it will travel in a time delta t, a distance delta S equal to half f delta t square. So if we compare this with this expression, we find that the effective acceleration is equal to 2 omega v. However, we have to remember that we are talking about vector quantities which have magnitude and direction. Let us now express this result in a vectorial form. Let us take first the fact that the angular velocity vector is directed vertically upwards as shown here, and the velocity outwards is directed like this. So we have two vectors, omega and v. What is the direction of omega cross v? That is obtained by using this screw, and this is a right-handed screw, and if I turn from omega towards v, I get it moving in this direction. So omega cross v is from O outwards, away from me, whereas the displacement was from A to B towards me. So there is a negative sign. So we can write f as a vector equal to minus 2 omega cross v. And correspondingly, the force which acts on the particle, the apparent force which pushes it from A to B, is given by F equal to minus 2m omega cross V, where m is the mass of the coin. This force appears in a rotating frame of reference provided the body has a relative motion in it. It is called Coriolis force after Gustave Gaspard Coriolis, a French engineer and mathematician of the 19th century, who discovered this formula in 1835.
As you know, our Earth is a rotating frame of reference, and so many things move on it, like a train, aeroplane, clouds, air, or a flowing stream. Now let's study the effect of Coriolis force on a flowing stream. Suppose this represents the northern hemisphere. Now the angular velocity vector of the rotation of Earth can be represented by this arrow. Let this represent a river, and we select this point for our study. The angular velocity vector of the rotation of Earth at this point is same as this. We represent this by this arrow, which is parallel to this arrow. The direction of flow of river can be represented by this arrow. The expression for Coriolis force is minus 2m omega cross v. In order to find out its direction, we have to find out the direction of omega cross v. For that, I'll use this screw. I'll rotate it from the direction of omega towards V. And as you can see, it points perpendicular to the plane containing omega and V into the globe. And so, minus 2m omega cross V will be exactly opposite to it, that is, in this direction. And this makes a certain angle with the direction of flow of water in the river. Now, if you take the component on the plane of the river, then it is towards the right of the direction of flow of water in the river. Now, it is because of this reason that the right banks of rivers are more eroded in northern hemisphere than the left banks. Now, suppose a river is flowing along the equator. What would be the effect of Coriolis force on the flow of water through that river? The direction of the angular velocity vector of the rotation of Earth at equator can be represented by this arrow, which is parallel to these arrows. Now, let us represent the direction of flow of river by this arrow. Now, once again, we will find out the direction of Coriolis force. The direction of omega cross V, as you can see, can be represented by the direction of advancement of this screw, which is into the globe and perpendicular to the plane of flow of water through this river. And the direction of Coriolis force will be opposite to it, that is in this direction, but once again perpendicular to the plane of flow of water through the river. So the effect of Coriolis force as regards eroding the banks of a river in equator is totally absent. Now, let us see the situation at the poles. Suppose a river is flowing in the poles and its direction is represented by this arrow. In order to find out the direction of omega cross V, I rotate a screw from omega towards V, and it advances towards the left with respect to the flow of water in the river. And the Coriolis force is opposite to it, that is towards the right and on the plane of the river. As we have seen that this force is perpendicular to the plane of the river at equator. So, its effect on either banks is nil. And then, at a point which is intermediate between equator and pole, this force makes a certain angle with the plane of the river. And its horizontal component is towards the right direction with respect to the flow of the river. So, the right banks are more eroded. And at pole, this force is in the horizontal plane, that is, on the plane of the river and towards its right. And so the effect of erosion is maximum at the North Pole. So this effect is minimum and nil at the equator, and it increases progressively as we move towards the North Pole, and is maximum at the North Pole. Now, a similar force acts on the air particles moving around in our atmosphere. Now suppose a low pressure zone is created in the Bay of Bengal. In such a situation, air from other parts will rush towards this zone, resulting in a storm. The Coriolis force will deflect the air particles towards the right. Now, if we look at this situation from a vantage point above, we will find air particles in the process of converging towards the low pressure zone will rotate in the counterclockwise direction, giving rise to a cyclone. This can be seen very clearly in the film taken by a satellite. Explanations of some natural phenomena have been provided on the basis of Coriolis force. In the expression of Coriolis force, omega happens to be the angular velocity of the concerned rotating frame of reference. For the examples that we have considered, omega is the angular velocity of Earth. Our Earth rotates about its axis. This was first experimentally demonstrated by J.B. Foucault in February 1851 at Pantheon in Paris. Now, what is this experiment all about?
Suppose this Mosambik represents the Earth and this pen represents a pendulum. If we make this pendulum swing on the north pole of the Earth, then because of the rotation of the Earth from west to east, the plane of oscillation of this pendulum appears to move from east to west. The Earth rotates through an angle of 360 degrees in 24 hours. Therefore, the plane of oscillation of the pendulum appears to rotate through an angle of 15 degrees per hour. If we repeat the experiment on the equator, we find that the plane of oscillation of the pendulum does not rotate at all, whether the pendulum is swinging in the east-west direction or in the north-south direction. The effect, therefore, progressively increases, being zero at the equator and maximum at the poles. Now, when Foucault performed this experiment in Paris, where the latitude is roughly 49 degrees. In fact, according to theoretical calculations, the plane of oscillation must turn through about 11 degrees per hour at Paris. Foucault could demonstrate that the plane of oscillation does indeed rotate by about 11 degrees per hour. In his pendulum, the mass of the bob was 28 kilograms and its length 70 meters. Inspired by the success of this experiment, it was repeated in several parts of the world, but none on such a massive scale as in this church in Great Britain. The pendulum was hung from the dome of the church. Its length was 82 meters and the bob weight 80 kilograms. The suspension was done by means of a ball bearing arrangement, so that the plane of oscillation of the pendulum was free to shift. However, we are trying it on a small scale here at Pune, which again has a low latitude, about 18.5 degrees. To ensure that it moves in a vertical plane and has no side movement, I must make sure that there is no twist in the suspension. Air resistance can cause damping, so we must have a mechanism which ensures that the pendulum keeps swinging for several hours non-stop. Now I will start the swing of the pendulum in the same way that Foucault did. As you see, it is now oscillating in the direction of this arrow. Calculation shows that in 1 hour, the plane of oscillation should rotate through an angle of 4 degrees 45 minutes, which means if I come back here in 4 hours' time, the plane of oscillation should have rotated through approximately 19 degrees, that is where I have put this second arrow.
The children have now all left. A girl is there with a pendulum. The merry-go-round is rotating and the pendulum is oscillating in a plane. Now let us see this situation from the point of view of a non-inertial observer. The merry-go-round now appears to be stationary and the plane of oscillation of the pendulum is changing. The same thing happens with our Earth. It is a rotating frame of reference like this merry-go-round.
As you see, the bob is now oscillating in the direction almost along this arrow which I had placed earlier, which shows that the plane of oscillation has turned through an angle approximately 19 degrees. We had seen that when a body moves relating to a rotating frame of reference, because of the Coriolis force on it, it moves sideways also. The same thing happens with the bob of this pendulum, which is oscillating. Because of the Coriolis force, its plane of oscillation gradually rotates. The great astronomers of yesteryears, Aristarchus of Samos in Greece and our Aryabhata, had to depend on the observations of the rising and setting of stars to conclude that our Earth spins around an axis. But the Foucault pendulum shows, even without looking at the cosmos, that our Earth spins round an axis, that it is a celestial merry-go-round that has been taking us for a ride for years and years.